Hi, this is Robin Andrews from CompUcademy, and this is a video about state transition diagrams and SR flip-flops and the ways that we can bring these two subjects together. So one of them is state transition diagrams, and the other one is flip-flops or latches. In this case, we're going to be discussing an SR flip-flop built using NOR gates. So what I've done is I've got some code here where I'm actually modeling the latch or the flip-flop as a finite state machine. And what that means is I've basically got a bunch of transitions here moving between different states. And I'll talk you through the code, show you how this works. So this is some code that we're importing that allows us to do this. That's in a separate file. Then we have a set of possible states. Now here I'm only really talking about the output of Q, or the value of Q. Normally these gates, these circuits give you Q bar, they give you the complement of Q as well, but that can always be inferred from the value of Q. So to keep things simple, I've just got Q equals 0, Q equals 1, or I've got an error state, which we can go into if we have a certain combination of inputs that you'll see later. Then we have the alphabet. Now that's the set of inputs for the machine. These are actually representing values of S and R. Now S stands for set and R stands for reset. And because this is a NOR gate, then we're talking about high voltages creating the action. So here a 1 for the S will activate the set condition, and a 1 for the R will activate the reset condition, i.e. revert the output of Q to 0. Hopefully that makes sense. These possible combinations of S and R are stored in a list here as our alphabet. That's the possible inputs for the machine. Then we have accepting states. So in this case, both Q equals 0 and Q equals 1 are perfectly valid states to be in. And then we have the initial state. Now you'd get different results if you had a different initial state, but let's assume now that the initial state is that the output at Q is 0. And then we have this line here, which is calling the constructor of the FSM class. So if you know a bit about object-oriented programming, you'll know what that means. Otherwise, basically, we're just creating a finite state machine that we can then add some transitions to. So the transitions are actually coming from the truth table. So let's see if I can find that quickly for you. Truth table for an SR latch. Okay, so Q. If Q, this is the initial state, so if Q is 0, then this set of SR values is going to create these outputs. But then if the initial state is 1, then you get a different behavior. So that's what makes these circuits different from the other circuits that you've seen so far probably, which are combinatorial. These are actually sequential. So what comes out actually depends on what went in before, or the state at the time that you give it this new input. Okay. So then, let's go back to our code. Let's have a look at the transitions. So you should be able to see, from this table that basically that's what the transitions are in my code. Okay, so I've got these definitions of transitions. If I'm in state Q equals 0, then I'll get 4 possible inputs at that state, and that gives me 4 outcomes, one of which is an error state. Okay, so with a NOR SR latch, if both the inputs are high, that's if S and R are high, it actually puts us into an error state because that is not a valid condition. And then looking at what happens when Q is initially 1, okay, we get a different set of behaviors for the same, so I'm not selecting very well, I can actually select using a bit more precision. So for the same set of inputs that I had previously, I'll get a different set of behaviors. Okay, a different set of end states from those transitions. And then I've got a bunch of transitions here dealing with the error state. So if we start in an error state, then regardless of what we put in, we remain in an error state. Okay. Now this can be represented in a state transition diagram, which I have here for this particular circuit. This one doesn't actually have the error state on, but hopefully it gives you some idea of how it works. Now, this might be difficult to understand because I'm basically taking 2 apparently separate concepts and I'm merging them. But I personally find doing that really helps me to get my head around both of them by seeing how each topic kind of applies in different parts of the syllabus. So it's worth spending some time really understanding, first of all, state transition diagrams, and then going back to SR latches and flip-flops, and then back to the state transition diagrams, making those connections, okay? So you can see here, I'll just talk you through it a little bit. If our initial state is 0, then inputs of 0, 1 or 0, 0 will both keep us in that same state, okay? And the output, that's the value of Q here, will be 0. However, if we're in a 0 state, so that means Q equals 0, and we input 1, 0, that's the only valid input we can have, then the output at Q will be 1, and will then be in state 1, okay? So we don't really need these outputs after our inputs with this / here, because in this particular case, that's the same as the state that we're moving into. And then when we're in state 1, inputs of 0, 0 or 1, 0 will keep us in the same state, but an input of 0, 1 will take us back to state 0. So that's the state transition diagram. What my code does basically is it enables me to define some transitions, which I'm doing here. Then I'm adding them to a list of transitions, and I'm adding those transitions, that list of transitions, to my finite state machine. Okay, so now the machine's been created, and all I have to do is I have to pass it some input. So what I've done here is I've got a sequence of input here, and I've taught you through what it does. Now remember, the input here, the first bit is the set value, or the S value, going into our machine. So yeah, the first digit is the S value going into our circuit, and the second digit is the R value going into our circuit. And as you can see, you have this feedback going on. So what comes out of this gate then gets fed back as an input into that gate. And that's what's special about these particular sequential circuits. So I pass in 1, 0, remembering that my initial state is Q equals 0. Okay, so that means here Q is 0. And then I pass in 1, 0, which means set, okay, for the NOR version of these gates. Remember, there is another version, which is the NAND version, which is inverted, but I'm not discussing that here. So this is the NOR version. So that means passing in 1, 0 will in fact be a set signal, okay? And then I'm resetting. So I'm passing in the second bit as 1, which resets the circuit. That should take it back to the state where Q equals 0, where the output of Q equals 0. And then I'm setting it again. And then this should do nothing, okay, because I'm not sending a signal to either the set or the reset part, okay, because the low voltages in this one do nothing. And then finally, I'm trying to set and reset at the same time, which obviously doesn't make any sense, and so should in fact produce an error, which it does. Let me just straighten my camera here. Seems to have gone a bit wonky. So all I have to do now is run my machine. And then finally, if I want to know if the final state is legal, then I can use the return value of calling that function. Now the code for this is all in a different file, like I said. So we're not looking at the details of how this is implemented. We're just assuming that the classes we've been given work correctly and then using them for our own purposes, which is really common practice when you're writing code, is you don't do everything from scratch. You can actually use pre-existing code, libraries, modules, etc. Finally, we need to actually run the code and see the result. So let's do that. Okay, I'll just talk you through this then. So we started with our initial state of Q equals 0. Then we input 1, 0. So that was a set signal, and that put us into state Q equals 1. Then we input a reset signal. That gave us state Q equals 0. Then we set it again, so just testing this functionality, and that put us to Q equals 1. Then we put in 0, 0, which in theory should have done nothing, which in fact it did. It left us in Q equals 1. And then we put in some invalid input, 1, 1, and that put us into an error state, and our final state was not legal. Okay, so that appears to be running correctly. So really that was just to show you the connection between some of these different ideas. So we've got the finite state machine, we've got the state transition diagrams, we've got these flip-flops or latches, SR flip-flops, and we've got a set of transitions, and all these disparate ideas are hopefully starting to kind of come together in your mind so that you can understand both of these main topics a little bit better. I may well include some of this code in a blog post later on, But for now, I just wanted to make a quick video to share some of these ideas with you. Okay, I hope that was helpful. Don't forget to subscribe to my channel if you find these videos helpful, and I'll see you next time.